This will be a brief introduction to Jade. I would have preferred to obviously do this in front of the class, but since we won't be able to do it, this is the best that I could do. So what I've done here is I've actually brought up a real pattern from a real customer of mine, and I'll go through a basic search match process and a basic Rietveld refinement just to kind of demonstrate how it works. And I'll try to show some of the attributes of the Rietveld refinement that were sort of highlighted in the slides. I don't know that it'll necessarily be easy to one-for-one reference the slides directly to what you might see in the Rietveld refinement in Jade, because they use different terms for some of the same thing. But regardless, we'll give you a better idea. Jade is the same package that is downstairs in the computer on the first floor in CCR. However, it's my understanding that we have a new version of it, so it might look a little bit different. But all the terms should probably look the same. So anyway, like I said, this is a real customer file that I've opened up. The first thing you would want to do to a pattern like this is fit it with a background. As I've indicated, most of the packages actually have an automatic background fitting program, if you will, and you can see that just by hitting that button, I've now introduced a background that kind of follows the bottom of the pattern. And you see little red dots. If you zoom in, you can see these dots, which are points that the software is actually put in to link the background. You can actually use this to vary the number of dots. As you can see, as I check these, the number of dots goes from a small amount on the right side to a large amount. Obviously, the more dots that you put in there, the more it sort of fits the background in tight to the troughs and inside the convolution areas of the peaks. As I think I said in class or in the last lecture, the background should really be a continual function all the way across the bottom. So typically you'll want to use sort of an intermediate number of spots. And then what you'll want to do is actually go through and review these spots and clean up the background a little bit. So I'll clean it up a little bit. I just kind of follow through. In general, the background should go through the noise in the X-ray diffraction pattern. That's pulling it down too far. And as I go through here, it actually looks like the software has done a pretty good job of fitting the background to this pattern. Okay, so that's a reasonably fit background, and that's what it should look like. So following this, we would now want to go through a search match routine on this. Unfortunately, I'm doing this from home over the weekend, so I do not actually have at home access to the PDF and the ICSD files that I would typically have at work because I have to pay for those and I don't want to pay for them at home. You can see that I actually had ICSD database on here at one point in time, but it since has expired. But I do have the COD, which is the Crystallographic Open Database, which we talked about, which, like I said, is free and for the most part will be sufficient for most of the general work people will do. So the COD is actually broken up into 9 smaller databases. And we're going to use COD9, which is primarily inorganic. It's primarily minerals. And this particular pattern consists mostly of minerals. Anyway, this is the basic phase ID search match text box to guide you through doing a search match. On the left-hand side are all the various databases you may or may not have. Like I said, we'll use the COD in this particular case. And then on the right side are various ways of filtering or accentuating the way the search match operates. Clearly, we don't have time to go through every single attribute of Jade or of the search match, but it'll give you a rough idea. Obviously, the most important is a chemistry filter. If we do a search match of every single element in every item of the database, a lot of times you'll tend to get some sort of silly matches or things that it's unlikely to be present. As I indicated, this is actually a mineral sample, so I'm going to check the use chemistry filter, and the C allows me to select common elements, so we'll select that, and for the most part, those elements will hit most of the minerals that are in the database. So we'll close that. So we're going to do a general search using that chemistry. I won't go through all this down here because we really don't have time. And then by pressing that button, it's going to go through and do a search match. As we previously discussed, it's going to do the search match on the 3 strongest peaks. And so it's completed its search match. And then you can see over here on this left window pane down here, we have a list of hits based on a figure of merit, with 0 being the highest and 99.9 or 100 being the worst, a list of potential hits. All right. And then what we'll want to do is actually sort of go down this list and look at the hits and make a decision whether these hits are accurate or not. This first hit, basanite, which is actually a calcium sulfate hemihydrate, so it's calcium sulfate with a half of water attached to it. You can see, looks like it's a very, very good hit. I mean, if you go through it peak by peak, we have good matches on all the significant peaks, and then you even go down to the very minor peaks, and you see that it fills in the peaks very, very nicely. Even some of these small little peaks here at 27.5 degrees and so forth. So that's probably a good hit. But right beneath it's anhydrite, all right, which is calcium sulfate without the half of water. And it might not be really surprising that such a similar mineral would have a very, very similar pattern. You can see if I toggle back and forth, the patterns are very similar, and you might be tempted to accept that anhydrite could be a hit. And depending on the quality of your pattern, it might be the case that anhydrite would actually come up as a preferred hit, and you might erroneously select anhydrite. And in fact, if you did select anhydrite into this pattern and do a Rietveld refinement, it would probably work reasonably well and actually provide you a quantity of anhydrite in the pattern. However, what you would hopefully see, though, is there would be several small peaks that would not fill in properly and would show up in the difference pattern, which I'll demonstrate in a minute. So when comparing these two, I think when you look down in the smaller peaks, down in these regions, and you go back and forth between anhydrite and basanite, it's fairly clear that basanite is the proper hit. So we're going to check that, and by doing that, it actually brings the basanite structure file into Jade so that we can do a Rietveld refinement. Now we still have a number of peaks that are unmatched, so we'll continue going down our list. And the third thing on the list is gypsum, which is also a calcium sulfate. In this case, it's calcium sulfate with 2 waters attached to it. So that kind of makes sense that we have a sample that consists of 2 different hydration states of calcium sulfate. So we'll go ahead and select that and bring that into the file. I certainly don't expect you to know what all the various buttons mean. This allows me to see everything we've selected at once. And for some unknown reason, it's not doing it. So we're going to get out of this and go back to our original Jade screen. And you can see that by checking those boxes, it's brought in the basanite, which are highlighted in blue. And you've brought in the gypsum, which is highlighted in red. And you can see that for the most part, we've accounted for, really what appears to be about 90% of this pattern. We do have one small peak here. I actually know from experience what it is just because of the position. And it's a very common mineral, but we'll go ahead and let the search match see if it can figure it out. One of the reasons, as I indicated earlier, that the search match relies on the 3 strongest peaks. We clearly have utilized the strongest peaks in this pattern. So the search match on the whole pattern is failing to identify that particular peak. So Jade does have built into it the ability to select peaks and mandate that that peak be brought into the search match. So we have a peak paint function, and I've actually specifically selected that peak now to be forced into the search match. We'll go back up here again, bring up a search match dialog. Everything is still set the way it was before, and we'll tell it to do a search match. This is just a note that says you can also zoom in as a way of changing what it search matches. So if I were to zoom in on a portion of the pattern, it would leave the peaks out that are left out of the zoom portion. But we'll go ahead and see what this does. And it goes through its search match. And the first match that it gives is graphite, which is actually a very good match. If I click on it, you'll see here are the sticks in this bottom area. I hope you guys can see this in this video. This particular stick has an arrow on it which indicates the strongest reflection. And if you look, I mean, there's certainly some kind of peak at every position. So graphite could actually be a hit in this particular sample. As we go down this, we also have boron nitride. All right, boron nitride and graphite are related in that they're basically the same structure. They're basically hexagonal structures it's a two-dimensional crystal structure with the two-dimensional layers laying on top of each other. So that's possibly a hit too. Again, you can see if I select it, there's its primary reflection, and the peaks are basically in the same spots. All right, we'll skip these additional graphite files and we'll go down here to quartz. And you can basically see that's slightly different, but its primary reflection is also in this position. And the rest of the reflections are actually too weak to even really see. There is a reasonably strong reflection right here, but you can see it's overlapped by this peak. So which one of the three is it? I'll save us some time and just go ahead and tell you that it's quartz. In most mineral samples, it's highly unlikely that you're going to get hexagonal boron nitride. That really isn't a mineral material. It could, in theory, be graphite, but it probably isn't graphite. The obvious way to check this would be to do some kind of chemical analysis. However, it's not uncommon for carbon to be in any kind of a mineral sample. But for the most part, mineral samples, again, just from experience, almost always have some amount of quartz in them just because quartz is so common. So just save us the time, I'm going to select quartz. And now we've fully analyzed the pattern. It's important before you do a Rietveld refinement that all the peaks in your pattern are fully accounted for. So you'll want to go through and do some kind of a perusal of the peaks. And little traced peaks, if you see stuff like this, really isn't that important. But you want to make sure any significant peak is properly identified. And as we go down this sample, we can see that all the peaks appear, properly identified, and we go all the way out to the end. Remember, out here, our peaks are starting to repeat, so we really aren't relying on the peaks out here too much. For the most part, we're really relying on the peaks from sort of 10 to 50 degrees to do most of our work. Okay, the first step in a Rietveld refinement. So I'm going to open up the Rietveld dialog here. And this dialog box is what comes up. Now, if you think of all the various terms that we saw in those various slides that represent the various parameters that we can refine, they actually are all here underneath these various tabs. Okay? As I'm sure you already figured out from the slides, there are actually far too many parameters for us to sit here and go through. But that does not mean that you, as somebody trying to characterize a material, cannot perform a Rietveld refinement and get out of it what you want. For the most part, most of the parameters have a default setting, and the default setting for most of the exotic parameters that you might refine are actually more than appropriate for 99.9% of the materials you might be trying to do a Rietveld refinement on. So just to make this look a little overwhelming, I'm going to actually tile this these tabs, and this basically exposes all the various switches and parameter settings that you can do in a Rietveld refinement in Jade. And in fact, there are even more underneath some of these things. If I were to press this, you'll see that there's actually a P2 value and S2 value, which are buried underneath this tab. There are multiple preferred orientation functions. There's various switches through here. And like I said, for the most part, I'm not going to go through most of these. I'm just going to go through sort of a simple demonstration of a Rietveld refinement, because we can, for the most part, rely on the default settings. Anyway, so the most important part of this dialog box is actually up here. And if I flip back to where it was before, oops, sorry, wrong button. All right, that's on the phase tab. All right, so on this tab, it defines the various parameters we're going to refine as it relates to each phase. If I pull this drop down or pull down, you can see there are my three phases: basanite, gypsum, and quartz. And for each one of those phases, we have, relative starting points. Okay. When I first opened the refinement from this options box, Jade automatically pulled the crystal structures from the crystal structure files in the database into Jade. So if the crystal structure already exists in the database, you don't need to provide the structure. And for the most part, that's what you're going to do. 99.9% of the refinement work that is done using existing structures. Where people are actually refining to obtain a structure, that's a little more exotic. But for what you guys wanting to quantify an X-ray diffraction pattern, this is what you're going to want to do. All right, and I'm going to back up a step. When I first open Jade or open this refinement box, it actually utilizes the peak heights and stick positions of the pattern as I bring them in. If I go over here and press this says list dialog. It opens up a dialog box which basically summarizes the 3 phases that I've brought in: basanite, gypsum, and quartz. All right, and then if you look over here, you see 2 columns here. One says 2T, which means 2 theta. This is actually a displacement, all right, that the search match did. And this is an adjustment to the lattice parameters in terms of the despacing, all right? So the stick patterns don't always exactly match the peaks 1 for 1. There's a certain error when it goes through and does a search match where it will allow a stick pattern to be selected, all right? On gypsum, you see that the search match actually inserted a displacement value of negative 0.04 degrees. Well, I'm going to turn that off, change that to 0. And you can't really see it, but if you notice, the gypsum sticks after I did that all shifted a little bit to the right, and they don't really line up with the peaks. Okay? So what that means is the lattice parameters for the gypsum are a little bit different for the real gypsum, for the gypsum in this sample, are a little bit different than the lattice parameters in the structure file that we brought in from the database. So to fix that, there's various buttons here. We're going to actually adjust the despacing until these peaks line up, or until the sticks line up with the peaks. And now you can see that they roughly line up. Okay, so if I open this again, you'll see that that's 0, and we've actually expanded the despacing, 1.0016 times, which is actually relatively small. Simultaneously, you also want these sticks to roughly relate to the height of the peaks. Okay, we really only have 1 quartz peak, so we're going to raise that to the very top of the peak. These are the 2 strongest reflections. The search match, by definition, brought those in for us and set them at the right scale, so they're roughly the right height. And if you look around, for the most part, the stick patterns match the peaks pretty well. However, the one exception to that is gypsum. Okay, and you'll notice, so that's saying that that's the primary reflection because there's a dot on the top. So that should be our strongest reflection for gypsum. However, you see that this is actually our strongest reflection. All right, why is that? And we discussed this 1,000 times in class. The reason for that is preferred orientation. And in fact, you can check whether that makes sense by going back to our overlay list of the various phases we have in here. And if you highlight the gypsum and double click on it, you will bring up the information that's in the card file. And here is a line listing of all the reflections and what their expected intensities are based on that reflection. So that's what should be the primary reflection, the 021. But you can see from the pattern that the 020 is actually the strongest reflection. And as it relates, and if you remember, you saw the pictures of gypsum in the SEM, all right, that 020 reflection reflects the fact that those those sticks are going to lay down flat like they do. So that's preferred orientation in this pattern. We will try to correct for that in the Rietveld refinement. So we can close this up. So I just want to kind of show that how these stick patterns are set up initially will be brought into the Rietveld refinement as a starting point. So we're going to open this up again. All right, I'm going to go to the Phase tab. And again, there are our 3 phases. So the first thing you want to do in a Rietveld refinement is choose a good starting point. Remember, this is a minimization process. You're trying to find a global minima. All right. The closer you are to that minima before you get there, the less likelihood there is of falling into a false minimum. All right, so you want to check and see how close you are based on the initial position of our sticks. And we have a button up here, and for what it's worth, I don't expect anybody in this class to actually remember these buttons or know how to go off and do it. Just understand that Rietveld is capable of doing this. All right, so if I go to this button, it says calculate XRD powder pattern. All right, and it's going to take those initial stick settings and it's going to generate a theoretical pattern. And there's our theoretical pattern that it's done based on all that information. All right, and then you can see up here at the top in brown is what's considered a difference pattern. All right, so this is the difference between our actual experimental pattern, which is here in black, and the pink curve, okay, which is generated from the structure files that we've brought in. And then here's the difference pattern. Can't really see the whole difference pattern, okay? But so there you go. So pink is experimental, and I'm sorry, black is experimental, and then pink is our modeled pattern. We talked about a little bit about this in class. Based on the shape of the difference pattern, you might be able to tell what parameters need to actually be refined. In this particular case, one, you can tell that the scale factor is too low, meaning the height of the peak is not sufficient, and it's not quite lined up very well, the modeled pattern with the experimental pattern, which creates this shape like that. This is the same type of shape. That means your lattice parameters are not correct. There's sort of a generally accepted process that you go through to do a refinement, and we talked about that briefly in one of the slides. You generally start with the scale factor and the lattice parameters, because those are sort of the obvious and easy ones. So the first thing we're going to do is turn off some of these things, except for the lattice parameters and the scale factor. So I can go check this all button. What this does is allow me to turn things off for everything. So I'm turning off these F0 and F1 boxes. What this does, just so you know, is the F series are the various full width half maxes. So this is our part of our profile fitting here. This is what determines the peak breadth. All right, so we're not going to deal with the peak breadth at first. We're just going to deal with the lattice parameters and the scale factor. All right, and if we toggle through the various phases, you'll see that F0 and F1 and F2 are off for all of those. Okay, we can unclick that again. And now this is our button to actually perform our Rietveld refinement. All right, we will leave all these checked. These are also profile parameters. This is the portion of it that's the Lorentzian portion of it. And then this is skewness and asymmetry in it, which we're not really going to talk about, just rely on the default. We did briefly mention the slides, various types of profile fits. So you could have a profile fit that's entirely Gaussian, you could have a profile fit that's entirely Lorentzian, or you can use either one of the two models, a Pearson 7 or a pseudo-Voigt, which are basically combinations of Gaussian and Lorentzian. In general, all peaks are some portion of Gaussian and Lorentzian, so you really want to use one of the combined models for doing profile fitting. I prefer Pearson 7, but you can try whichever one works best for you. In any case, so like I said, lattice constants, scale factor, and we're going to actually do our first refinement of this pattern. And then you can see it's going through various rounds, an iteration, and then you saw round numbers. All right, what the round numbers are, if you look on the sides of some of these parameters, you'll see a round assignment. Sorry. So that's the second round. This is done in the third round. What that means is it's actually doing the refinement in steps. If it converges in the first round of something, okay, it'll converge and stop, and it won't even refine the lattice constants, or in this particular case, skewness, or Lorentz and the polarization factors, all right? So it starts with sort of the obvious things, and then works to sort of the deeper things. You can see the thing that here is round one, is our scale factor. Then in round two, it does the lattice constants. And then in round 3 and 4 and so forth, it goes to sort of the deeper things. You generally do refine the full width half max in the first round, but I decided to leave that off just to sort of see what we got. Okay. Now we can go off and look at the initial results. You can see that the difference pattern up here has actually gotten quite a bit better Just to kind of make things a little more clear, I'm going to cut off the high angle stuff. All right, and you can see we have some intensity differences here, a substantial intensity difference here, an intensity difference here and here. Note that primarily the intensity differences relate to the gypsum, which you can't really see it on here, but that's the red sticks. The blue sticks is the basanite, and then the green is the quartz. Note the quartz fits very nicely. Quartz in general actually behaves very nicely as a phase, and the refinements are generally pretty straightforward. Anyway, that's reasonable, but we really want to clean up the peak shape a little bit, which is the profile. So what we're going to do is we're going to turn on F0 for all three of our phases, which is our full width half max. This is going to actually allow the modeled peaks to either become wider or narrower as necessary. The reason we have F0, F1, and F2 is if you highlight that, it's actually defining full width half max as a function. So you can define this function as F0, which is a constant, plus F1 times 2 theta plus F2 times 2 theta squared. All right, you can decide how far you want to take this model, if you will. In general, for phases that have very low quantities, say 10% or less, you generally want to just make it constant across the entire pattern because the minor peaks are too small to really properly fit. If you're above 10% or a major phase, you generally will want to refine F1 and F2 because the peak breadth will follow this relationship across the pattern. So right up here in this box actually shows our initial weight percent calculations based on our first refinement. And if we go through them, so it's saying we're about 55% gypsum, we're about 3% quartz, and we're about 42% of basanite. All right. Realistically, this really isn't as bad as it might look, even though the difference pattern looks pretty bad. These numbers are probably not that far off. And by the way, down here at the bottom is an R value. This is the residual error. This is basically the difference between our experimental pattern and our calculated pattern divided by the overall intensity. So it's generally accepted that for something to be publication quality, that value needs to be better than 10%. But you can tell from looking at this pattern that we should actually be able to improve that R value anyway. So I would not, looking at all these differences, not be comfortable using this. So the first thing we're going to do is, like I said, click on F0 for all of them, and then let's go ahead and click on F1 and F2 for the high quantity phases, which is the gypsum and the basanite, and we're going to refine it again. And you can see that it's done a reasonable job of cleaning it up, right? We don't have anything which is really indicative of a profile problem. So next thing we're going to try to do is deal with some of these intensity issues, okay? Primarily in the gypsum. So down here is a button that says PC. That's preferred orientation correction. We're going to check that box, okay? And it's going to default to a pull direction. All right, notice the minute I checked this box, it dropped in 021. 021 was that expected primary reflection, which is this reflection. But the preferred orientation is really probably in this 020 direction. So we're going to want to fix this and change this to 020. Okay, and then we're going to run our refinement again. And see, it's going through its rounds. All right, it said refinement halted. All right, that means it basically couldn't find a better minimum than where it was. And if you go down, look at the difference pattern. This looks okay. This looks okay. Okay, we do have a little bit of an intensity issue here. We have a little bit of an intensity issue here. And you can kind of go down this. All in all, this actually really looks pretty good. All right, the next thing we can do, we're sort of out of things to refine here. So the next level that we could do is actually let the atomic positions move. All right, so they might be slightly different in their position than the structure file that was brought in here. So we can open up this and you get this rather complicated box which shows various atomic positions. This is the fill, so this is how much it actually fills up that position. This is the actual position, and then this B value is actually the temperature value. If I press the C button, it's going to actually it's going to automatically check all the atomic positions for me and allow me to refine those. So I'm going to let them move a little bit as part of the refinement. All right, and we really haven't made much of an improvement. Now, sometimes you get yourself in a false minimum, and I mentioned that. This kind of refined, I mean, it came up and said refinement converged. Okay, by the way, notice the R is already better than 4%, but we still have a couple of wonky looking peaks here with the basanite. So let's go do the same thing with the basanite and let those positions move a little bit. And what I'm going to do is I'm going to reset all these values by just changing the profile and then changing the profile back, because these are all profile parameters. And notice it reset all those values. And I'm going to start our refinement again. And don't worry about all these things that I'm sort of ignoring. And you can see, so it's going through its rounds. And hopefully with all of these, parameters properly selected, we should get a reasonable refinement. And that's pretty good. So we have an R value of 2.77, and you can look at the various parts of the different pattern. And I mean, you do see some differences, but these differences are all relatively small, and they clearly somewhat offset. Obviously, if you have differences that are substantially over or substantially under, that will mean your quantification will probably be substantially over or substantially under. And that's a basic refinement right there. If you wanted, for whatever reason, to know what the structure actually is, how much it changed, you can at this point actually export the structure, okay, into a CIF file, which is a crystallographic information file, and actually look at the actual values in terms of refined structure. All right, if you remember initially we talked about that the ultimate goal of a Rietveld refinement is to get to a structure solution. And so you've gotten there, so you have that. And of course you have lattice parameters here too. So obviously if you're doing some kind of a doping study and you want to see if the doping study affects your lattice parameters, you might take 3 different samples with 3 different doping levels, and you would look at these lattice parameters and you would measure the lattice parameters using X-ray diffraction, do a Rietveld refine them and then on them, and then compare the lattice parameters across those different levels of doping. Anyway, we do have an output, so there is a report generator. Create new report. Say yes. Overwrite the existing one, and there's a report. There's actually a dozen switches to report some things, not report others. I obviously can't go through them all, but this is just sort of a basic report, so it sort of tells the various things that you've chosen to refine. Here's your profile refinements. We've refined sample displacement, but there is any, all right, so it looked for sample displacement. 0.001 degrees is almost no sample displacement. I'm not going to go through all of these. And then it goes through for each phase and shows the results of our refinement. So here are your lattice parameters, your A lattice parameter, B and C. Here are the corresponding angles here, all right? And here in parentheses, of course, are your error for those calculations. Here's your scale factor, all right? And then we have our various F values. If you obviously want to know what the full width half max of your peaks are, you would have to actually calculate this in this case using this relationship, the full width half max of any peak based on the 2 theta position. There is actually a switch when you generate the report which will give you the full width half max of each peak calculated. I just don't have that switch checked. So there's our basanite. There's phase 2. There's our gypsum. Again, lattice parameters, our angles, our scale factor. There's our preferred orientation correction. By the way, we didn't really talk about it in here. This is a March-Delossy preferred orientation correction. That's the name of the method. But in JADE, If this value is 1, it means there was really no preferred orientation. As that number goes down, it's basically going to pull down the pole direction that you've selected, which is 020 in this particular case. Again, there's our full width half max values. And then last but not least is quartz. In these two cases up here, we have very low symmetry crystal structures, which is why we have an A, a B, and a C, an A, a B, and a C, and different angles. Quartz is hexagonal. All right, so we just have an A and a C value. The B is the same as A. Of course, the angles are 90 and 120, so they're unchanged. And we did not select F1 and F2, so F0 is just a constant. So for the quartz, we held the peak breadth at 0.09 degrees across the entire pattern. And then down here is a summary of our quantitative analysis, 44, 52, and 3% for the various phases. And then this is actually the equivalent RIR that the Rietveld refinement determined based on the parameters that we used. Right? So if you were going to go off and try to do an RIR, you could use these values and see if you could get to the same place. By definition, it also does a crystallite size and strain analysis. I think I indicated that that's really only good up to 100 to 200 nanometers, depending on the instrument parameters. So in this particular case, it gave a full width half max of basanite of being 268 nanometers. It gave gypsum 101 nanometers. And for this one, it really didn't have enough peaks to do a proper evaluation, so it would have just done it off this peak, this one at 26.2 degrees. So it did this greater than 1,000. Unfortunately, we didn't really have time to talk about instrument parameters. The instrument parameter it used was a full width half max of 0.1 degrees as a constant. And that's actually a really large number. So realistically, with a number like that, these are really not good once you get to 100 nanometers. So realistically, you really couldn't report these values and have any real meaning. Here's your final R value. So you had a residual error of 2.77%, which is really very good. And then as a side bonus, it actually provides the equivalent XRF calculation. It's very common to do X-ray diffraction and X-ray fluorescence at the same time to sort of complement or supplement each other. If you had a large amorphous component to this sample, you might be able to use the X-ray fluorescence summary to relate back to an XRF analysis and get some understanding of what your amorphous component's actually made of. That's really it. If people have questions or want to see a demonstration like this again, please let me know. But that's a quick and dirty Rietveld refinement.